Welcome to our summer enrichment program. We are here with Reed Johnson, and he's going to tell us about um, his career and how he does what he does on the topic of robotics and machine learning. Welcome, Reed.
Yeah, thanks for having me. As Patrick said, my name is Reed Johnson. I'll give you a little bit of my background. So, about me, I first started in robotics in college. I've been working in the industry to some extent for the last 8 years. I got my bachelor's of science in mechanical engineering at the University of Minnesota. I went on to get my master's of science in mechanical engineering with an emphasis on robotics right after. I kind of specialize in electromechanical systems. My master's thesis was on unmanned ground vehicles, which I'll show a little bit about. As well as machine visions, and these span all sorts of industries, healthcare, medical devices, manufacturing, all across the technology industry, essentially. So right now, I am a solutions engineer at a company called Boone Logic, which I'll talk about sort of at the end here. So I'm going to show a little video of my first robot. So I made this in college. My high school didn't have a robotics program or anything like that. So my first exposure to robotics was in college. So I took a robotics class in college, and this is the first thing I made here. So it's called the Trident, but basically it's just got servo motors. It's powered or controlled by an Arduino, and then it draws the letter M. So this was the first robot I ever made. It was fun, and that's really what got me excited, and kind of just set the tone for the rest of my career until where I am today. So I'll just fast forward here. Basically, pick it up, just a poorly written M. But I'll show the top here. Powered by a couple batteries, an Arduino, and a few servo motors. And it's pretty cool what you can build with a few cheap parts and struggling your way through code. So after that, my first internship was at a 3D printing company. So that kind of helped me propel me further into the robotics field. So I worked on 3D printers. I worked on the mechanical design of the extruders, as well as a little programming experience, because what is robotics without programming? So this just helped me further kind of my expertise and my understanding in the field as my first internships. And then I started working in a medical robotics and devices lab at the University of Minnesota. This was one of my first projects. Basically, in the background there, you can see a robotic arm. And this robotic arm has this attachment, this black attachment. We're looking at the left figure. And on that attachment is some cameras, as well as a printer head that you would find in your household printer, was mounted, an inkjet head there mounted in the middle. And this was programmed to follow your hand, and then spit out ink onto your hand, in the Minnesota M, block M there. So you can see down here on the left and see actual printing there. It's not the best, but it was fun. That's actually my hand. That ink didn't come off for weeks, but that just kind of helped solidify my knowledge here. Hand is moving, the camera is telling where that hand is, and then it's telling the robot, hey, you need to move to follow this hand. So this is using computer vision techniques to track that hand. And once the robot says, hey, I'm in the right place, then we start 3D printing onto the hand. This is just a fast forward version of what it's doing, and it's really only spitting tiny dots each moment until it spits enough ink dots to make that block M there.
And will it follow the hand if it moves in the middle?
Yep. So definitely, once the hand starts moving, it will follow it. For the purpose of the video, we just try to keep it still, and it produces a little bit better results. But yeah, the idea is that you can move the hand all the way around. This thing will follow it, and it will print that block M. And you might ask, what is the purpose of this? And it's all building towards something. This was kind of a stepping stone. So that was back in 2016. That was, gosh, 7 years ago. We need to play that. Let's go into the next one. Here we, instead of using a robotic arm, we're using an XYZ gantry system. So similar to what your 3D printer might have. This is a version of that type of robot. And on it, instead of ink, we're printing a biogel, which could be used for various different medical applications. So burn victims, whatever it might be. This gel can also be layered, kind of like your normal 3D printers. You have layers of stuff. So this gel can do the same sort of thing. I'll play this video here. So it's tracking the hand. This camera, let's see if I can remove that. Right here is what is providing the frames, feeding it back to a computer where we have computer vision algorithms saying, hey, here's the hand and here's where you should print. This green laser here is telling you how high. It's basically giving you feedback on the height of this printer head right here with the blue ink or blue gel. It's just giving you height feedback. So that's what this green line is doing. So this was for a conference paper, IROS, and basically we created a research paper, submitted it, and now it's in a medical journal. So this is the third layer. So as I mentioned, you can do layers. You can see over here where the robot is and where it's continuing to print, and it will just follow and print until that layer is done. I think we did 3 layers. You could do however many layers you want, but that is kind of the outcome of this. We have some metric values here. But yeah, so that was in 2017, about a year later at the Medical Robotics and Devices Lab. Let's move on to the next one. We go on more and more. We get a little bit more complex. I don't have too much about this one, but this is a 3D printed gantry. Now this little guy down here, you can think of a hand moving around in 3D space. This one also does rotation. So instead of a hand, we have another moving platform, but the idea is the same. Being able to track objects and 3D print onto them as they're moving in space without a known trajectory. So using cameras as visual feedback, computer vision, all these sorts of things to create, a bio 3D printer on moving targets. It was a really fun project. And that was in 2017. 2017 is when I graduated with my undergraduate degree. And then I started my master's degree. So after working in the Medical Robotics Devices Lab on 3D printing robots, I made what is called Junior Robot. Now it started off as just a companion robot. All it did was follow you around. But on it, it's kind of interesting in robotics. You can use off-the-shelf parts, weird parts. So this on the top here, we have an Xbox 360, I think it was called the Kinect camera. Basically, we can use that, take it off a gaming system, put it on a robot, and take the output, the camera frames, to do something interesting. So on there, we had a display. On that display, we would have like a face, a smiling face or something like that. And then in the front here, we just have like a little distance sensor acting as a bumper, kind of like a Roomba might. So this one basically in this video, all it does is it's tracking a human. It sees a person, and then once it sees a person, it just clings onto them and follows them around. So it doesn't do anything, terribly interesting, but it just follows you around. We call it the companion robot, aka Junior, your little buddy.
What did you use to train the robot to recognize and follow people?
Yeah. So this one we didn't have to actually train anything. What we're doing is we're taking those image frames and we're looking for basically a human like skin. So it's not a machine learning model, but basically there's computer vision techniques to find like the skeleton of someone. So basically, if you look in behind the scenes here, what the computer is actually seeing is an outline of my limbs, like the center of my mass, in the distance I am away. And it's saying, hey, I'm going to point myself at your center of mass. And then I'm going to try to keep like a meter away from you. And whenever you move, I'm just going to follow you. So this one wasn't actually using machine learning, but just some simple computer vision.
Were you
techniques.
able to use the functionality of the Kinects?
Yes. Yep. So that is people. The nice thing is a little bit about this robot is one, there's a little, it's called an outboard. It's kind of like a fancier Arduino, if you will, that has a little bit more memory and compute power. But people write Python libraries, which a lot of this code is written in Python, that take the output and they utilize some of what the Kinect outputs as well. So the Kinect will actually pre-process a lot of that for you internally and output, an exoskeleton or something like that. So we were able to utilize that using Python. So as I'm making these projects, I am, gaining more knowledge in robot systems. What do you need compute wise, sensor wise, reliability wise, as well as tuning your skills in programming. So C++, Python, those are, the most popular right now, I would say, in robotics. But there's certainly a bunch of other languages that have their uses. Yeah. Let's see if there we go. Moving on from there. So after my undergrad degree, I started working at a company called Danfoss. Danfoss, for the most part, manufactures a bunch of different parts for automobiles, tractors, whatever. But they internally wanted a robotics group to start getting into autonomous vehicles. So myself and a few others at Danfoss were on this team. And our first goal was to make a Danfoss autonomous utility tractor. So on the left here, this is a John Deere tractor. And basically what we did is we painted it white. We added red to it because John Deere is normally green. We got the shroud here. We made a custom shroud out of fiberglass, put it over the cockpit where a normal person would sit. We added sensors such as, you can kind of see on the top here, GPS, high accuracy GPS. And on the front, which you can't really see, is a LiDAR. So the LiDAR is giving you a 3D point cloud of your surroundings. The GPS is giving you a location. And I think we have a camera on there as well, just to give you an idea of your spatial surroundings and what you can do. So this was kind of my first, go back here, step from more hobbyist level robots to something much more high quality and expensive and fun. So this is a little promotional video. It's kind of silly, but it just shows the idea of a autonomous tractor. Which we call Davis.
Morning.
So this is a silly idea, but basically Davis is in the background. And whoever produced this thought it'd be funny if Davis, the autonomous tractor, went and stole this guy's breakfast off a pallet.
Morning, Davis.
You're up early.
So that's the gist of it. It's a silly promotional video, but this was one of the funner projects I've worked on. This was built here, actually in Plymouth, Minnesota. We shipped it to Norway, where it's done a bunch of demonstrations, and now it's still there to this day. So that one uses cameras for computer vision, high accuracy GPS sensors, LiDAR, field of distance sensors, and a compute module, basically just a high-powered computer to process everything and control it. So yeah,
So I have to ask, for the promotional
yeah.
video, was that autonomous or controlled?
So the part where they like turned it on and it looks like it's waking up and whatnot, that was controlled. But when it goes and picks up that pallet and then backs up, that was autonomous. So what we did is basically for the demo purposes, that was what it did. It went and picked up pallets and put things down. So that part was autonomous. So half. But yeah, I always think that's kind of silly the way they set that up. But the whole idea is to convey that, hey, autonomous tractors can be very useful and possible in agriculture. So obviously stealing people's breakfast is not a useful task, but we also demonstrated with this, doing certain things around farm and agricultural environments, plowing, whatever you can use with the tractor, which is a lot of different things you can use with a utility tractor like that. That was back in 2017. To this day, they've still worked on their capabilities, and now they do a lot of different autonomous farm type stuff, such as like digging trenches, planting seeds, whatever you can think of. They're working on making autonomous, which is pretty cool. And in the agricultural field, we got a question here. What kind of safety features do you have to build in? So luckily, we had the fun part. This was a proof of concept, and when you're working on proof of concepts, you get to be a little bit more lenient on the safety features. As it's going into production, you obviously have to be a lot more conscious of it. But there's a few things that you assume when you're working with something like this. So in this video, there's going to be someone in the corner with a wireless emergency stop button. So they always have their finger on it. And in some cases, a couple people will have these buttons that if anything goes rogue, you hit this safety stop button, power gets disconnected to everything, basically shutting down the robot. So, I mean, that's a good question. I think in the future, or after I was quit being involved with it, you use the LiDAR. So the LiDAR is a 3D point cloud. And basically, whenever an object is within a foot that is not supposed to be there, then you either avoid that object, move away, or just stop. So yeah, that's a great question. There's a lot of different ways you can apply safety. One is always just having an emergency stop. Two is utilizing the sensors and avoiding or moving away from things that shouldn't be there. Yeah, good question. Let's see, we will move on. So in my master's degree, I TA'd for a robotics course, really fun. We made a robotics lab, basically using a 6 degree of freedom robotic arm that students had a lot of fun with. So let me see if I can actually pull up a video here. One sec, there's an ad and I'll share my screen to this. Oh, here we go. All right, I gotta switch my screen here. 1 second. Window and here. Let's see. So this is robotic arm. Robotic arms are used a lot in manufacturing. This is a cobot. So basically what that means is that this robotic arm, it has the motors that move the joints, but then it has a lot of safety features. So if I were to go push up against the robot knows internally, hey, that shouldn't be there. I'm going to stop moving. So to avoid from moving and hitting someone. So we had students, basically the final project was we bought these cheap flashlights that break down into 4 parts, and they have to use the robotic in this pneumatic chuck over here, which you'll see being used to reassemble the flashlight. So you're understanding the robot. You get an idea for basically, I need to go to XYZ, and what does that mean in terms of the robotic arm angles, inverse kinematics is what we call it. So you can see it's figuring out, okay, this is the body of the flashlight. It will spin. You can actually fast forward here. We don't need to watch all of this. Basically, you got to spin threaded on all the way. And then in there, it has a little torque sensor. So when you're threading it, once it's threaded all the way, it will start resisting. And you need to program the robot to realize when that's happening and when it's threaded. And when that torque spikes, the resistance spikes, you say, okay, this is threaded on all the way. Time now, like that, time for the battery. So now you have to go pick up the battery, position it, drop it in like so, and then pick up the back of it and then thread that on. Until it's all the way on, pick it up and then drop it off. And then when it's all said and done, you should be able to pick it up and turn it on. So
I
that was a
noticed
fun project.
I noticed that when it started turning to threads, it would
Yep.
it went back and forth a lot. I'm guessing that it was looking
Yep.
for a small amount of resistance to know when it was make sure it wasn't cross threading.
Yep, that's exactly right. So when we give this problem to the students, it's an open-ended thing. You have some students that are doing, 760 degree of movement. But when that happens, you cross thread. These are cheap flashlights and you can cross thread them pretty easily. So yeah, little movements, you're looking that you're not cross threading. So yeah, that's a good point. Yeah, let me flip back over to my slides here. Here, share again. Yeah, so that is that. This is just, I won't go into too much detail. This is my first robot, was that Trident one. This is a hex robot. It can move really quick in 3D space. And these sort of things are actually used a lot in manufacturing as well. Pick and place. So if you have an assembly line, you see that things are going down a conveyor and you need to straighten them out or move them or sort them. These robots are very popular in manufacturing. I don't have a fun video for that, but that is one of them I worked on. Moving on, still at Danfoss, we worked on autonomous airplane cargo loaders. So these are the things if you go to Minneapolis or any airport, you look for these machines right here that basically load and unload cargo into airplanes. You'll see a bunch of these at every airport. So we worked with the company to basically take these machines and make the whole process autonomous. So what that means is it finds these machines sit out on the tarmac. It finds open airplane cargo doors. It plots a path to that door, and then it drives up to it all autonomously without anyone intervening. So, and the reason is apparently that there's a big cost when these operators actually run into the airplanes and cause all sorts of damage. So they came to us and said, hey, can we make this autonomous? And our group said, yeah, we think so. I'll have to stop sharing again to show this video. Sorry. Let's see here. Let me reshare. Here we go. So this was with the company that manufactures. They wanted an autonomous solution. So basically in the bottom right here, part of the process to doing this is creating a simulation environment. So simulation environments and simulations are huge in robotics. It's much easier to create simulated robots and sensors and test them out and get a good idea and understanding what you need. before building them or having the real life one and kind of developing alongside having a physical one and a simulation one. And the simulations, you can basically do whatever you want. It's okay to break the simulation robots because you can just restart. It's better to break a simulation robot than it is an actual robot. So in the bottom right here, you can see a simulation one. Basically, we built this in a program called Unity, which can give you really realistic environments. It's used a lot in computer vision. Basically, just allows you to render simulated environments that look very, very real. So we created a simulation environment, and we would basically plot one of these cargo loaders in the tarmac and just hey, go dock to this door. So that's what you're seeing here. And now this is the real life one. So this was down in Orlando, Florida. They made this little poorly mocked up version of the side of an airplane. So I got a question here from John. Was there something in your sim environment that you didn't account for that surprised you when you got to the real environment? Yes. So that's a great question. I love that question. There absolutely was. So on this robot, let me see if I can actually back up here. Let's see. Just reverse. So right here, you can see my cursor. We have a LiDAR, which is basically sending out light. Light is returning, and it tells you how far things are away. So LiDAR works really well in almost every environment. When you see a real shiny side of an airplane like this, light doesn't return that well. So when we were in the simulation environment on the left here, we have this matte white surface. The LiDAR is returning in the simulation environment very well. When we got there, it's like we're missing half of our point cloud. The light's not returning for this LiDAR, and it threw us up a lot. So yes, that's a great point. In simulated environments, they're only as good as you allow them to be. If you don't factor for things like that, which is something we would have never thought of, you're going to run into issues and problems on your real life robot. So yeah, I love that question. So you can see it here. It's monitoring, it's driving, it's steering until it gets to the door. So that's all I have in that video. But that was a real fun project. It was down in Orlando, and we were there in the summer, so it was very hot. And one of a bee made a nest in the machine, so it was hot, and there was a lot of bees. So that was the only downside to that. Let's see. There we go. So that was one of my last main projects with Danfoss. They continued to do a lot of different things, different robots, autonomous vehicles. A lot of people would come to us and say, hey, we have this vehicle. Before we send it out, we have to do testing on it. We have to put 100 miles on it and make sure it doesn't break down. So what we would do is create an autonomous rig that would drive around that vehicle for them before they can, release it to customers or anything like that. So, and this sort of robotics, the autonomous vehicle field, you get a few main things: computer vision, obviously. So Tesla's, which I'll show in a minute here, use solely computer vision. Then there's other autonomous vehicles that are relying more on LiDAR, so 3D point clouds rather than computer vision, because computer vision can be very tricky when lighting changes. You could throw off your computer vision model, etc. So we'll get a little bit into that. Then here is my Husky. This is my master's thesis. So this was a robot that had a 16-channel LiDAR, a very, very high accuracy GPS, radar, IMU, which is basically gives you heading, and a few other things. So this was my thesis. I worked on it for years. And basically at the end of my thesis, what it was able to do is this robot was able to drive and map sidewalks in urban neighborhoods. So the LiDAR would tell you, hey, here's grass, here's a sidewalk, here's someone's driveway, and basically create a map of sidewalks in navigatable areas in neighborhoods. So this was a really expensive robot. My professor was able to create funds, but this robot right here, it's not huge, but it probably costs in the area of $150,000. All these sensors and devices, they're not cheap, but they're really fun to play with. So I like that a lot. I don't have a cool video here at all. Well, I wish I did, but yeah. So that's it for this robot.
Was there a use case for this particular robot, or was your thesis more about the sensors and capabilities?
Yeah, there was a use case, or building towards a use case, I should say. So this sort of thing could be used for a few things. Is package delivery. So you've probably seen like DoorDash, Uber. They're using these robots that drive on sidewalks and navigate, deliver your groceries or whatever it is. So that sort of thing could be, this technology could be applied to that, as well as we were working with a sector of the U of M that worked on providing a more accessible world. So this could be used for someone in a wheelchair able to navigate on sidewalks and help them move about the environment. So that was kind of leaning towards that as well. I don't have much on this. This is actually patent pending, some of this work, so I can't unfortunately show too much about the background stuff. But yeah, there's a few applications that still could be possibly useful for. This is basically my engineering design process, which I've used throughout this is applied to more mechanical stuff, but it basically just say, hey, when you get something like this and you look at the end product, like, how could I ever build this, do this? Like, there's all these different moving parts and whatnot. It seems very overwhelming, but what I like to do is you have to break it down to something that is more bite-sized and manageable, and that makes sense. So basically, when I am doing something, I'll just touch on this quick. You got to brainstorm, and then you research, experiment. You're just playing around. You're not taking it too seriously until you fine tune your idea, and then you go into the prototype phase where you're actually building and making it a reality and physical. And then you troubleshoot with the scientific method. Does this work? What doesn't work? And kind of put all those little pieces together until you have a final build. I know this probably doesn't make too much sense, but it's just when you see complex systems, if you break them down, they're not that difficult when you just take it one step at a time. And that's what a process that I've had to train myself to do to kind of help build some of these systems. Moving on, so that was robotics. Let's get into the more machine learning part. So the past 4 years, I've worked at Boone Logic, which is a machine learning company in Minneapolis, Minnesota. And we do all sorts of machine learning for different applications, which I'll get into, but let's just get an overview of machine learning. So there are many types of machine learning. There's the main three, and there's obviously more than that. There's unsupervised learning, which is things such as clustering, dimensionality reduction. This is not what you imagine in computer vision, where you're labeling. So you get a picture of a dog and a cat, and there's a bounding box of a dog and a cat with labels on it. That is supervised learning. So that would be something as classification. Also, regression is supervised learning, and that is kind of, market forecasting. The stock has done this today. What do I think it's going to do tomorrow? That's a regression problem, and that would be a supervised learning task, which is supervised meaning, hey, I'm helping the algorithm by providing these labels. So it is learning off a data set of cat images that I said are cat images. Unsupervised learning doesn't need that hand holding. It doesn't need the labeling. Basically, you're just feeding it raw data, and the unsupervised algorithm is processing it and making sense of it. That's things where clustering comes into play, where clustering is just saying, hey, this data is similar, and this one differs from that set of data. So you don't need labels to do that. Finally, there's reinforcement learning, which is, I'll show a cool video on that. But basically, reinforcement learning is saying, hey, I'm going to try a task and I'm going to fail or succeed, and I'm just going to try that task millions, billions of times, and I'm going to learn from it. So I have a cool video on that. That's just kind of a summary. Here's a different way to look at it. Supervised learning, classification, regression. Unsupervised clustering is basically just saying, these green dots are different from the red, which are different from the blue. They're clustering in different segments. Reinforcement is saying, hey, I have an agent, I have something moving about an environment, I'm getting feedback for my action, which will make a lot more sense here when I play this video. The company I work at right now is primarily unsupervised learning. So we take raw data and we make sense of it and provide analytical insights, which I'll kind of end with at the end here. The machine learning process is basically you have data. So you have a bunch of camera images, you have current data coming off of a robot. You feed it to a machine learning model. That model is developing, it's making sense of this data. In the example of cat classification, it's knowing what images contain cats and what images don't. So when I'm given an unknown image, I'm looking in that image to see if there's a cat in there. That's what developing the model and training that model means. And then test and analysis. Once you get a model, you don't know if it's good or not. You have insights, there's indication whether it's good or not, but test and analysis is saying, I'm feeding you new data that you didn't train off of. How well are you doing? So if I give you a picture of a dog, are you not classifying that as a cat? Are you able to do that? So you're testing that. And then you go live with it. You put it out into production. You have the world use your algorithm. A little bit on the machine learning hardware. There's a lot of different things out there. Machine learning, for the most part, not always, requires a lot of compute power. So your laptops have CPU, which is like Intel, ARM processors. This is a CPU that does a lot of your processing on your computers. Some laptops, gaming computers, have GPUs. Those are graphic processing units, which help you do a lot of matrix calculations and really fast. So GPUs are incredibly common in machine learning. You have FPGAs, which are field programmable gate arrays, and these are even faster than GPUs in certain applications. And then you have things such as TPUs, which are just even bigger graphics GPUs. And the world of hardware to support these machine learning algorithms is ever evolving and getting bigger and bigger. But to train things such as, I'm sure we all know what ChatGPT is, requires an insane amount of compute power. And they're able to leverage things such as AWS, where they have server rooms of all this stuff, and they can utilize all this compute power and build models faster. But I can't do that when I'm working on my laptop. I'm only constrained to my one CPU or GPU that is in my laptop. So this is a supervised learning example. So this is actually what this is, the Tesla's autopilot, what it's seeing. So you're seeing all these lines, you're seeing these little markers here, and what Tesla has made is a extremely robust set of machine learning computer vision models that is able to detect so many things. So you can see these road markers here. It's using that camera image. It has a machine learning model that says, hey, these are lanes in a road. This is a car in front of me. This is a stop sign. So it's very impressive, this model that Tesla has built. It's not always perfect, as you see in the news sometimes, but it's actually very, very, very incredible. It's wild that they can do all of this on board a car.
Interestingly, so
Yeah.
this is a really interesting visual and an interesting video. Last week, we talked with somebody who works for Danso, who is doing exactly this sort of thing. So
Sure.
a little bit, a very small amount of familiarity just based on the descriptions, but it's very cool actually being able to see this.
Yeah, and it's wild when you see Teslas up out in their environment. They look very sleek, but there's a lot going on inside, and this is one of the things people think of Tesla as a car company. but they are so much more. They are a technology company that is doing something like this, and in its own is very, very impressive. So they have probably the most robust autopilot autonomous car when it comes to computer vision solely. It's definitely Tesla. There's other ones that are using lidars, which give you a point cloud of the environment, which Tesla doesn't do. It's just guessing, not guessing. It's taking those images and saying, hey, this is a car that is 8 meters away, where a lidar is going to tell you exactly that car is 7.3 meters away. But Tesla has to do it all through computer vision, which is pretty cool. Move on to this one. This one I'm not going to show the whole video, but this is reinforcement learning.
Dear fellow scholars,
are you able to hear the audio through this at all? When the video
this is
plays?
2-minute papers
Yeah,
Maybe
yeah,
not.
we can.
Oh yeah, okay.
with Karo
So this is a
Zsolnai
really
Fehér.
cool
In this project,
reinforcement
OpenAI
learning.
built a hide-and-seek game for
So I pause here. So this is a hide and seek game. The red guys are trying to find the blue guys.
pit.
So this is reinforcement learning, and it's just basically they start from ground zero, and then these agents, the blue and red guys, learn how to navigate the world and play the game. So they can grab and move objects. They can do all of this.
You'll see in a moment. These agents learn from previous experiences, and to the surprise of no one, for the first few million rounds, we start out with pandemonium.
So if you heard that, it's the first few million rounds, and they do millions, if not billions, of rounds of simulations for reinforcement learning. It's insane how many trials they take, and each trial they are learning something. They're adding on, but it's just little bits that you're adding on each trial.
Everyone just running around aimlessly. Without proper strategy and semi-random movements, the seekers are favored and hence win the majority of the games. Nothing to see here. Then, over time, the hiders learn to lock out the seekers.
So now the hiders are saying, how can we win this game? How can we stop them from beating us? So what they do is through reinforcement learning, they're realizing they can pick up these boxes and block the doorway. You think that's okay,
by
game
blocking
over,
the doors off
but now the seekers
with these boxes and started winning
can
consistently.
learn how to
I
manipulate.
think the coolest part about this is that the map was deliberately designed by the OpenAI scientists to succeed.
So what the seekers
they cannot
are going
win
to start
alone,
doing,
and hence they are forced to learn to work together quite well. But
there's
then,
this ramp over here, and eventually after millions more
something
trials,
happened. Did you notice this pointy
realize
doorstop?
that,
Problems later,
hey,
the
what
AI
happens if we
also
take this
discovered
ramp
that it can be pushed
and jump over
near a
this wall,
and be used as
and they do that, and now they start winning again.
If so, how? Well,
so do this through reinforcement learning, and it seems very impressive, but you got to realize it takes millions and millions of simulations and trial runs to do this. Let's see. Getting to the end here. Let's see if this plays for us. Looks like that's frozen. Anyway, we'll move on. But
Hang on a sec. You're glitching a little bit. Let's let it catch up.
Learning. It's very cool, very impressive. Eventually, they learn how to break the physics of the game. Let's see. I'll move on from this slide. Let's see. Is this one now?
You're a little choppy right now.
This AI-based predictive analytics.
This is very cool. Can you hear me? I think he's having problems with his connection. Okay, Prem can hear.
Ah, shoot.
That's okay. I think you're having problems with your connection a little bit. This game is really, really interesting in the fact that it takes millions of revisions to reinforce this model and for it to find solutions that work is kind of amazing. Looks like Reed's dropped out. I'm guessing he's going to try and rejoin. Let's give him a minute here. So what do you guys think so far? Any questions in the chat?
I think it's really cool. Did you say how long each one of these, like, you know, hide and seek matches lasted? I know you said like there are lots of them, but did he say how long?
He
All right, sorry
didn't.
about
That's okay.
my camera.
So the question is, with the simulations, with the hide and seek game, do we have any idea how long each iteration took?
Yeah, so I don't know off the top of my head. I think they actually say in that video. So I will send the link to anyone that's interested. But I think this took a long time. Obviously, that simulation is sped up. You know, they can do that one trial in probably less than a second. But for visualization purposes, they played it in real time. So I'm not sure, but I can send that video out. It's one of my favorite videos.
That's a great video.
Yeah. I'll finish here. So this is my current company. We do unsupervised machine learning in a bunch of different fields. So basically what we do is people come to us with data, so sensor data. So if you go in a manufacturing environment, there is every sort of asset, conveyor, robotic arm has a bunch of data, temperature, current, whatever, flowing. And for a lot of people, it's an overwhelming amount of data. What do we do with it? We create an easy solution to do unsupervised learning, make sense of that data so you don't have to take time to label it. Basically, you just feed it into this unsupervised algorithm and it gives you analytic results back, basically telling you, is your asset healthy? So we work in a lot of different fields, you know, video surveillance to quality assurance to sensor-based predictive analytics. We have a few applications, an automated visual system. Yes, telemetry, yep. Which means basically just sensors, you know, temperature sensor, a current sensor, whatever it may be. And then we have an unsupervised learning algorithm for predictive maintenance. So predictive maintenance, meaning there's a few different maintenance ways. There's one thing people call usually just break fix. So I'm only going to fix this asset, this whatever it is, once it breaks. There's preventative maintenance, which is usually on like a time base. So I'm going to replace the bearing in this asset and every 3 months or something like that. So that's preventative. And then there's predictive, is saying, hey, I'm going to run this asset until I start getting told that, you know, something abnormal is happening, and then I might replace that. But I'm going to keep that bearing in there until I'm told it's not good anymore. So that's predictive maintenance. So we do stuff like that. We're running out of time, but basically what this allows people to do is give you weak notice when your asset, your marine engine, whatever it may be, is starting to act abnormal. So here in this plot, so you can see if you have a temperature sensor and that sensor is recording data once a minute for months, the historical plot of that sensor might look something like this. And you can do the same for pressure sensors, speed sensors, torque sensors. Basically, what you can do is feed that raw data into an algorithm, and it's going to learn what is normal. This is what a normal temperature value is when the pressure sensor is this, so on and so forth. When the speed is going this is what the temperature should be. So an unsupervised algorithm can understand that to a very, very precise level, much more than a human ever could. So that's what our algorithm does. It makes sense of this raw data. It learns from it. It learns what's normal. And basically, we have out there a lot of people use dashboards to say, hey, how compliant or what is my asset? Is it healthy right now? We have ways of telling them, no, your asset isn't healthy, and here's the sensor that is causing the problem, and you should have a maintenance technician or whoever it is go look at that part of the robot or the engine. So I'll just keep going through here. I'll show an example here. So this is a centrifugal compressor. John asks, how do you store so much data? Do you store all the raw historical data? So the answer is yes and no. It depends on the application. Some companies, and we leave it up to the company we're working with. So some companies want all data from forever, which can cost a lot of storage. So one solution is putting it up into the cloud, into Amazon, AWS, or Azure, Microsoft, and they can essentially store unlimited data. So that's one solution, is just storing it in the cloud where your storage size can be very, very, very large. Or else you just say, hey, you guys have a lot of data. We are going to, after 3 months, that data is just going to be deleted. So you kind of have a streaming window of data that they can store, inside their office or something like that on their hard drives. But you're much more limited in that aspect. So it kind of depends on the client there. This is a compressor. So basically what we did is we took the data coming from this compressor. We learned what is normal. Again, this is a little boring, but basically the healthy score of this compressor started dropping. They took it apart, they looked inside, and they actually found it was very minor, but there's this tear right here. This piece was actually breaking on this cooling bundle, and these little shards in here. And they said they actually expected this asset to fully malfunction in about a month or so. From these little parts were going to make their way down the system and actually just disrupt the asset entirely. They were able to fix it pretty easily through this. So it can detect small things like this through machine learning that to a human, it's something you just would not be able to pick up on. This is another one of our more exciting application is instead of using sensors, temperature sensors, whatever it may be, you can use cameras. So basically, we're using a series of cameras. Hey, here's what a normal vial that's free of defects. It doesn't have any cracks, doesn't have any particles in it. And then learn what a normal vial is. When an abnormal vial that has a crack, that has a defect comes along, the algorithm says, hey, this is abnormal. Let's see if we show it here. Yeah, this is abnormal, and this should be removed from the assembly line. So you can do that with unsupervised machine learning very easily. And then lastly here is moving back to a robot arm example. You have this robot arm current values are coming from this, and we are learning what throughout this motion, what are the normal current values for all the motors in this robot arm. So basically we learn what's normal, and we put different weights in it. So basically this is a current value, and we're learning these sensor waves essentially. And then if you were to take a weight that it didn't learn, so it's used to carrying a 5-pound weight and a 10-pound weight. What happens when you put 15 pounds on it, or 7.5? That should be flagged as an anomaly because it shouldn't be carrying that sort of weight. What happens when you put that in there? So you can see here as it's moving about, it's saying, hey, I have an abnormal weight. And you can do it very quickly without having to do, you can see here, this red is the abnormal weight, and it sits between these two lines that are deemed normal by the algorithm, but a human wouldn't be able to do that. You can't do that with thresholds because it sits between two variations of normal. So on supervised machine learning can pick out these minor little details that would either take a lot of time to build customly. It can do, in sometimes a matter of a few minutes. I think that's the last thing I have here. Yeah, so that is kind of just the summary of my journey through robotics and machine learning and the different types of applications you might encounter doing that. So that's all I have. And is there any final questions or comments?
You may have said this already, but is there anything in particular that got you interested in going down this career path?
Yeah, and I like that question a lot because I actually started college wanting to be an orthopedic surgeon. So I was on a pre-med path my first year of college, and I realized I really didn't like chemistry or biology, which is not good if you want to be in the medical field. So, and then I took my first robotics class, which I built my first robot, and I just got hooked. It just hit me like that. So after I made my first robot, I was able to use my hands building mechanical systems and motors, and giving it a brain through a microcontroller. I just got hooked on it. So after I built my first robot, I was like, this is what I want to do with my life. So, and it didn't happen gradually. We didn't have a robotics class in high school, which I wish we did. But I just got exposed to it in college, and ever since I started doing it, I knew it was my thing. The first program is big in Michigan. Were you aware of that? So I am aware now. In high school, I was not aware of the first program, and I think my high school that I went now has a robotics program, which is good. I love it. But yeah, we didn't have it at the time, so that's an awesome program. I'm so happy people are able to build these skills in high school, middle school, wherever they start. It's very important, especially in today's age where the world is becoming more automated and robots are becoming more of our life. So yeah, it's a good field to be in. John asked what my favorite CAD program is. That's a good question. I started with, I think it's still called PTC Creo. That's what we learned in college. Ever since I got into the real world with a job, I use SolidWorks, and I love SolidWorks a lot more than Creo. But to each their own. They're all, for the most part, a little bit similar. But my favorite is definitely SolidWorks.
Okay. Any other last minute questions?
Not that I could think of. Thank you for presenting to us.
Yeah, of course. Thanks for having me. It's fun.
Thank you, Reed. This was great. Fantastic information. Like I said, let me toss this back up on the chat. We are recording this. We are going to pretty it up and put it out on YouTube. There's a playlist out there now. The playlist is URL is in the chat. So it should be out there within a day or so for anybody who missed all or some. Please share widely. This is the fourth of the fifth for this, the 5 that we have scheduled for this year. And hopefully we'll be able to continue doing a lot more of these because this is absolutely fantastic. So thank you again, Reed. I greatly appreciate your time.
My pleasure. Yeah, thanks for having me.
Yep. All right. Thank you, everybody.
Awesome. Thanks, guys.
Thank you.